Science. 17. Quantum mechanics. Quantum mechanics, probing the subatomic world. Wave-particle duality. Wave-particle duality is a fundamental concept in quantum mechanics that reveals the dual nature of particles. It states that particles, such as electrons and photons, can exhibit both particle-like and wave-like characteristics depending on the experimental context. This concept revolutionized our understanding of light and matter, as it challenged the classical notion that particles and waves were distinct entities. The wave-like nature of particles is evident in phenomena such as diffraction and interference, where particles exhibit wave-like behavior, while their particle-like nature is observed in phenomena like particle detection and measurement. Wave-particle duality forms the basis of quantum mechanics and is crucial for explaining the behavior of subatomic particles. Uncertainty principle. The uncertainty principle, formulated by Werner Heisenberg, is a fundamental principle of quantum mechanics that states that the more precisely the position of a particle is known, the less precisely its momentum can be measured, and vice versa. This principle highlights the inherent limitations in simultaneously determining certain pairs of physical properties with absolute precision. It implies that there is a fundamental uncertainty in the measurements of complementary variables, such as position and momentum or energy and time. The uncertainty principle has profound implications for the nature of reality at the microscopic level and challenges the deterministic worldview of classical physics. Superposition. Superposition is a fascinating principle in quantum mechanics that allows particles to exist in multiple states simultaneously until they are observed or measured. According to this principle, particles can be in a combination or superposition of different quantum states, rather than being limited to a single well-defined state. This concept is exemplified by the famous thought experiment known as Schrödinger's cat, where a cat is considered to be both alive and dead until its state is observed. Superposition lies at the heart of quantum computing, where quantum bits, qubits, can represent multiple states simultaneously, enabling parallel computation and the potential for exponential computational speedup. Quantum entanglement. Quantum entanglement is a phenomenon in which two or more particles become correlated in such a way that their quantum states are intimately linked, regardless of the physical distance between them. When particles are entangled, the measurement or manipulation of one particle instantaneously affects the state of the other, even if they are separated by vast distances. This non-local connection between entangled particles challenges our classical understanding of cause and effect and has been experimentally confirmed through various tests, including the violation of Bell's inequalities. Quantum entanglement is being explored for applications in quantum communication, quantum cryptography, and the development of quantum networks. Schrödinger's cat. Schrödinger's cat is a thought experiment devised by physicist Erwin Schrödinger to illustrate the concept of superposition and its implications for quantum measurement. In the thought experiment, a hypothetical cat is placed in a sealed box along with a radioactive substance that has a 50% chance of decaying within a specific time. According to quantum mechanics, until the box is opened and the cat is observed, it is considered to be in a superposition of both alive and dead states, representing the indeterminate state of the radioactive substance. The thought experiment highlights the peculiar nature of quantum superposition and raises questions about the role of observation and measurement in collapsing quantum states. Although Schrödinger's cat is a theoretical construct, it has become a popular metaphor for understanding quantum measurement and the challenges it poses to classical intuition. Quantum tunneling. Quantum tunneling is a phenomenon in which particles can pass through potential energy barriers that, according to classical physics, should be impenetrable. In quantum mechanics, particles are described by wave functions, and these waves can extend into regions of space where classical particles would not have sufficient energy to reach. Consequently, particles can tunnel through energy barriers, appearing on the other side without requiring the classical energy to overcome them. Quantum tunneling has significant applications in various fields, such as semiconductors, where it allows electrons to move through thin insulating layers, and in scanning tunneling microscopes, which rely on the tunneling of electrons to image surfaces at the atomic scale. The phenomenon of quantum tunneling challenges our classical understanding of particle behavior and plays a crucial role in numerous technological advancements. Quantum field theory. Quantum field theory, QFT, is a theoretical framework that combines quantum mechanics with special relativity to provide a comprehensive description of the fundamental particles and the forces that govern their interactions. QFT describes particles as excitations of underlying quantum fields that pervade all of spacetime. These fields are subject to quantization, resulting in the creation and annihilation of particles. QFT successfully explains the behavior of elementary particles, such as electrons, photons, and quarks, and provides a unified understanding of electromagnetic, weak, and strong nuclear forces through the exchange of force-carrying particles known as gauge bosons. QFT is the foundation of the Standard Model of particle physics and has been instrumental in predicting and explaining various phenomena observed in high-energy physics experiments. Quantum computing. Quantum computing is a rapidly advancing field that explores the use of quantum mechanical principles, such as superposition and entanglement, to perform computational tasks more efficiently than classical computers. Unlike classical bits, which can represent either A0 or A1, quantum bits or qubits can exist in superpositions of both 0 and 1 simultaneously. This property allows quantum computers to perform parallel computations and potentially solve complex problems much faster than classical computers. Quantum computing holds promise in areas such as cryptography, optimization, drug discovery, and simulations of quantum systems. However, the development of practical quantum computers faces significant challenges, including the need for precise control over qubits and the mitigation of quantum errors. Quantum teleportation. Quantum teleportation is a quantum communication protocol that enables the transfer of quantum information from one location to another without physically transporting the quantum state itself. It relies on the principles of quantum entanglement and quantum measurement to transfer the quantum state of one particle, known as the sender or the teleportee, to another distant particle, known as the receiver or the teleporter. Quantum teleportation has the potential for secure communication since any attempt to intercept or measure the transmitted information would disrupt the delicate quantum state. While quantum teleportation has been successfully demonstrated in experimental settings, practical applications are still under development, with potential applications in quantum cryptography and quantum networks. Quantum gravity and string theory. Quantum gravity is a theoretical framework that aims to reconcile the principles of quantum mechanics with the theory of general relativity, which describes gravity on a macroscopic scale. The quest for a theory of quantum gravity seeks to understand the behavior of gravity at the smallest scales, such as those encountered near black holes or during the early moments of the universe. String theory is a leading candidate for a theory of quantum gravity, proposing that fundamental particles are not point-like entities but rather tiny, vibrating strings. String theory harmonizes quantum mechanics and general relativity and suggests that the universe exists in more than 3 spatial dimensions. Exploring quantum gravity and string theory has the potential to revolutionize our understanding of the fundamental nature of space, time, and the universe itself. The Copenhagen interpretation. The Copenhagen interpretation is one of the most widely accepted interpretations of quantum mechanics, developed primarily by Niels Bohr and Werner Heisenberg. It postulates that the act of observation or measurement causes the collapse of the wave function, determining the definite state of a quantum system. According to this interpretation, before measurement, particles exist in superpositions of all possible states, but upon observation, the wave function collapses to a single state, resulting in a definite measurement outcome. The Copenhagen interpretation emphasizes the probabilistic nature of quantum mechanics and the role of the observer in determining the measurement result. Although alternative interpretations have been proposed, the Copenhagen interpretation remains a cornerstone of quantum theory. The many worlds interpretation. The many worlds interpretation, proposed by Hugh Everett III, offers an alternative perspective on the nature of reality in quantum mechanics. It suggests that every possible outcome of a quantum measurement actually occurs in separate, coexisting universes, commonly referred to as branches or parallel worlds. According to this interpretation, when a measurement is made, the observer and the measured system become entangled, resulting in the emergence of multiple parallel universes, each corresponding to a different measurement outcome. In the many worlds interpretation, rather than a collapse of the wave function, all possible outcomes coexist in separate branches of reality. This interpretation challenges traditional notions of reality and has sparked debates about the nature of measurement and the existence of parallel universes. Quantum electrodynamics, QED. Quantum electrodynamics is a quantum field theory that describes the electromagnetic force and the interactions between charged particles and photons. It successfully merges quantum mechanics with special relativity to explain phenomena such as light-matter interactions, the behavior of electrons in electric and magnetic fields, and the emission and absorption of photons. QED provides a comprehensive framework for understanding the behavior of electromagnetic fields and particles, enabling highly precise predictions of measurable quantities. It is one of the most successful and well-tested theories in physics, laying the foundation for subsequent quantum field theories, including the electroweak theory and the quantum chromodynamics, QCD, theory. Spin. Spin is an intrinsic property of particles in quantum mechanics that is unrelated to any classical analog. It is a form of angular momentum that particles possess, even if they do not physically rotate. Spin is quantized, meaning it can only take certain discrete values, such as 1/2, 1, 3/2, and so on. The spin of particles influences their behavior and interactions, contributing to phenomena such as magnetism and the Pauli exclusion principle. Spin plays a crucial role in determining the energy levels and the allowed states of particles in atoms, nuclei, and subatomic particles. Understanding spin is essential for grasping the fundamental properties of particles and their interactions within the quantum world. Quantum cryptography. Quantum cryptography is a field that harnesses quantum mechanical principles to provide secure communication protocols that are resistant to eavesdropping and interception. Quantum cryptography takes advantage of the fundamental properties of quantum mechanics, such as the uncertainty principle and quantum entanglement, to enable secure key distribution and encryption. One example is quantum key distribution, QKD, where encryption keys are shared using entangled quantum states. Any attempt to intercept or measure the quantum states during transmission would disturb the delicate entanglement, alerting the legitimate users to the presence of an eavesdropper. Quantum cryptography has the potential to provide unbreakable encryption methods, ensuring secure communication in the face of advancing classical cryptographic attacks. Quantum biology. Quantum biology is an emerging interdisciplinary field that investigates the presence and role of quantum phenomena in biological systems. It explores how quantum effects, such as coherent energy transfer, quantum tunneling, and entanglement, might play a role in fundamental biological processes, including photosynthesis, enzyme catalysis, and bird navigation. Quantum biology challenges the classical view that biological systems can be fully understood using classical physics and chemistry alone. By integrating quantum mechanics into the study of biological processes, researchers aim to gain insights into the efficiency, robustness, and sensitivity exhibited by living organisms. Quantum biology has the potential to revolutionize our understanding of life's fundamental processes and inspire new technological applications. Bell's theorem. Bell's theorem is a groundbreaking result in quantum physics that demonstrates the impossibility of explaining the correlations between entangled particles using local hidden variable theories. It asserts that certain quantum predictions, such as those described by entanglement, are fundamentally incompatible with local realism, which assumes that physical properties exist independently of measurement and are predetermined. Experimental tests of Bell's inequality have consistently shown results that violate the bounds imposed by local realism, providing strong evidence for the non-local nature of entangled particles. Bell's theorem has significant implications for our understanding of the nature of reality and has sparked ongoing debates about the philosophical foundations of quantum mechanics. Quantum thermodynamics. Quantum thermodynamics is a field that studies the behavior of heat, energy, and work on the quantum level. It extends the principles of classical thermodynamics to quantum systems, accounting for phenomena such as energy quantization, fluctuations, and coherence. Quantum thermodynamics aims to refine our understanding of the laws of thermodynamics and their application to microscopic systems, where quantum effects dominate. This field investigates topics such as quantum heat engines, quantum refrigeration, and quantum information processing using thermodynamic principles. Quantum thermodynamics provides insights into the fundamental limits and possibilities of energy conversion and utilization at the quantum scale. Feynman's path integral formulation. Feynman's path integral formulation is a powerful mathematical framework in quantum mechanics that offers a distinct perspective on the behavior of particles. It introduces the concept of a particle taking all possible paths between 2 points, rather than following a single well-defined trajectory. According to this formulation, the probability of a particle transitioning from an initial state to a final state is obtained by summing the contributions of all possible paths. Feynman's path integral formulation has been instrumental in calculating transition amplitudes and probabilities in quantum mechanics, enabling precise predictions and calculations in quantum field theories and quantum electrodynamics. The pilot wave theory. The pilot wave theory, also known as de Broglie-Bohm theory, is an alternative interpretation of quantum mechanics that reintroduces determinism and realism into the quantum world. It proposes that particles are guided by a hidden pilot wave that determines their behavior and paths. According to this interpretation, the wave function provides information about the probable positions of particles, and the pilot wave guides the particles along well-defined trajectories. The pilot wave theory challenges the conventional understanding of quantum mechanics, which emphasizes the probabilistic nature of particles and their wave-like behavior. Although the pilot wave theory is a minority interpretation, it offers an alternative perspective on the nature of quantum phenomena and raises questions about the fundamental nature of particles and their interactions. Quantum cosmology. Quantum cosmology is the application of quantum mechanics to the study of the universe as a whole, particularly in relation to the origin, evolution, and fundamental nature of the cosmos. It aims to address questions about the nature of space-time, the initial conditions of the universe, and the behavior of matter and energy on cosmic scales. Quantum cosmology investigates the application of quantum principles to cosmological models, such as the Big Bang theory, inflationary models, and the study of cosmic microwave background radiation. By combining quantum mechanics and general relativity, quantum cosmology seeks to provide a unified description of the universe, offering insights into the fundamental nature of reality and the mysteries of the early universe. Thanks for watching. Please like, share and subscribe, and comment below if you agree, or would like to add your thoughts.